Hey, I'm Ansh Bansal, and today I'll be talking about refraction. Let's get started. In simple terms, refraction is defined as the bending of light rays when they go from one medium to another. We observe three possible cases with refraction, and I will show you these cases with the help of this diagram. In this diagram, you can see the interface between two mediums as well as a dotted line called the normal. The normal is an imaginary line that we draw perpendicular to the interface between two mediums. Let's proceed. In case 1, we have light rays going from an optically rarer to an optically denser medium. In this case, the light rays bend towards the normal after refraction. In case 2, we have light rays going from an optically denser to an optically rarer medium. In this case, the light rays bend away from the normal after refraction. In case 3, we have light rays going through two mediums having the same optical density. In this case, the light rays pass on straight through and do not bend. Note that optical density is completely unrelated to mass density and is dependent on a medium's index of refraction. When light rays go from one medium to another, they encounter a change in their speeds. They either go faster or slower in the new medium, depending on the new medium's optical density. To account for this change in speed, the light rays optimize their paths so that they can still get across to the other side in the most minimal amount of time. Because the light rays change their paths, they bend. So that's why refraction occurs. A great example of refraction in everyday life is when you put a straw in water. When light rays reach the interface between air and water, their speeds change. That causes them to bend, and that makes it look like the straw has either been magnified or has been split into two. The index of refraction, also called refractive index, gives a measure of how much the speed of light changes and how much the light rays bend when going from medium 1 to medium 2. The index of refraction can be represented by two letters, n or the Greek letter mu. We can calculate the index of refraction of one medium with respect to another using these equations. You can pause the video and take a look at them yourself. Today we'll be looking at the last two equations, which state that n21 is equal to n2 divided by n1, and n21 is equal to sin I divided by sin r. You can see what these terms mean on the right-hand side of your screen. Let's apply these equations in a demonstration to find the absolute refractive index of a material. In other words, the refractive index of that material with respect to air. Here, I have a ray box with a slit, a glass slab, and a way to measure angles. In this system, the glass slab is medium 1 and air is medium 2. You can see when I put the light at an angle of about 30 degrees with the normal, or angle of incidence, the angle of refraction is about 51 degrees. Let's do some math and find out the absolute refractive index of this glass slab. Here, we calculate the absolute index of refraction of glass to be about 1.55. This is about 3.3% off from the real value, which is 1.5. We know that when light rays go from an optically denser to an optically rarer medium, they bend away from the normal. Here, as we increase the angle of incidence, the angle of refraction also increases. At a certain measurement of the incidence angle, the angle of refraction becomes 90 degrees. This value of the incidence angle is called the critical angle of those two mediums. You can find the formula for critical angle right here. As we increase the incidence angle past the critical angle, instead of going into the second medium and refracting, the light rays reflect back into the same medium. This phenomenon is known as total internal reflection. Let's look at a demonstration. Here, we have light rays going from an optically denser medium, glass, to an optically rarer medium, air. As I start to increase the angle of incidence, the angle of refraction increases as well. As I approach an incidence angle of about 40 degrees, the angle of refraction starts to become 90. And just here, when the angle of incidence is about 42 degrees, the rays of light reflect back into the same medium. This is total internal reflection, and that means the critical angle is just under 42 degrees. Let's do the math. Here, using the formula for critical angle, we find it to be just about 41.8 degrees. This perfectly matches our estimation of being just under 42 degrees. That's pretty cool. Thank you for watching. I hope you enjoyed learning about refraction.